Okay, welcome everybody. Okay, does anybody have any questions before we start? Okay, then let's start. Last week we were talking about correlation, so let's go there now. And just in case, I guess I should. Here. Okay, so let's go there now. So suppose we have this picture, and suppose that, let me just make a copy of this for the time being. Okay, so suppose we have a picture like this, and we have some data. So we have a dot here, and a dot here, and a dot here, and a dot here, dot here, dot here, dot here, dot here, and so on. So if this is what our data looks like, we can ask a question: is the y value related to the x value? So let's write that. Is, in this case, husband's salary related to wife salary? So what we mean by that is, first of all, we could find the average first. Let's say we could find the average husband salary. We could also find the average wife salary. And we would or could use those to guess the salary of a randomly selected person. So we could say randomly select a wife and guess what her salary is. So that would mean that each of these, remember we said that each of these dots represents a couple, and so the x coordinate of each of these dots is the wife's salary. So we can see that we have, maybe I drew, let's say I have n, maybe I have 30 dots there. So let's say I have 30 dots there. That means I have 30 couples. And if I have 30 couples, that also means I have 30 wives. And so I could just collect all of the wives' salaries. That just means reading the x-axis for, the x coordinate for each of these dots. So then I would have a bunch of wives' salaries. I could put them in a set. For example, I could have the first one, maybe the first one is $50,000, the next one is $60,000. Next one is $80,000, and so on. So I could just collect all of them, and I would have 30 numbers here for the 30 salaries of the wives. And then I could easily take those numbers and calculate the mean. And suppose I calculate the mean, and the mean is, let's just make up a number, the mean is $60,000. And let's say that right here is the $60,000 mark. Let's say here, sorry, right here is the $60,000 mark. So a lot of the salaries are less than 60,000, wives' salaries, and a lot of the salaries are more than 60,000. So, and then we could do exactly the same thing with the husband. And let's say this is the husband, and let's say the husband is 80,000 is the mean. Okay, so we could do this. And so if that's all the information you had, if you didn't have this picture, you didn't have these green dots, you just knew that the mean for the wife is 60, and you also knew that the mean for the husband is 80. And then I said, okay, now I'm going to go out on the street and find a couple, and I'm going to ask that couple, I'm going to speak to the wife. I'm going to say, what's your, and I'm going to ask you, not her, I'm going to ask you, the students here, I'm going to say, what would you guess is the wife's salary? So here, randomly select a wife and guess what her salary is. So let me ask somebody what your answer would be to this. So let me ask Ho Young Chang. So what would your answer be to that question?
$40.
Sorry, what did you say?
$40.
40? Why 40? $40? Okay, I don't think 40 would be right, but okay, that's a guess. Let's see, somebody else? How about this person? Jovan. What would you guess?
60.
60, right? Because the average wife's salary is 60. So why would you guess something else? Right? It would be kind of strange to guess, oh, well, I'll guess, this wife, her salary is 100. No, I don't think so. Why should I guess 100 when the average is 60? I don't really have any reason to guess anything other than 60. So you would guess 60 for the wife, and you would guess 80 for the husband. So we drew last time these lines. So I'll do it. I think I did one was darker green. I'll do that like this. One was that color. Well, actually, I shouldn't use that color. Let's use a different color. I'll use oops. Try this color. I'll try this color. And what happened to that? How do I do this? Sorry. I'll use this one here. Where is it? Can't get this to work. Okay, here. Okay, so I'll draw a line here. So that's kind of like where the wife is. And then I'll have a different color for where the husband is, like this. Okay. So suppose that's the mean for the wife and the mean for the husband. Okay, now suppose that you can see this data You can see these big green dots here. And now I'm going to ask you for the husband's salary, but I'm going to give you a little more information about the couple. I'm going to say that I'm talking about a couple where the wife's salary is here. So if the wife's salary is there, so let's say that's 20,000. So suppose we have a couple where the wife's salary is 20,000, and now I ask you to predict the husband's salary. So probably you're not going to say 80 anymore. So what might you say instead? Somebody, let me ask somebody. How about this person? Jinho Seo.
Yes, Professor.
What would you say about the husband's salary now? Are you going to guess that it's 80 now?
No, sir.
What will you guess instead? No? Okay, let me ask somebody else. How about Jung Kyung Lee? What would you guess instead? What did you say?
Sorry, Professor. I don't know.
Okay. How about Sayaka Yoshimura? What would you guess instead?
Maybe 30 or 40.
Okay, good. Because we said, suppose we know that the wife's salary is 20 now, what would you guess the husband's salary is? So if I hadn't told you the wife's salary was 20, the best guess would be 80 for the husband. But now I'm telling you that the wife's salary is 20, and now somebody says, okay, I'm going to guess that the husband's salary is, like she said, I think 30 or something like that. So it might be right. That might be a good guess. Anyway, it would be better than 80. So why did we change? Why did we change our guess? So how about if the data had looked like not this picture, but this picture?
Professor, I have a question.
Yeah.
So previous graph, can you show previous graph?
Well, let me just finish this and then you can ask the question. Okay, suppose the data look like this, but we still have the same lines here, 60 and 80. So we still have here, we still have 60. What color did I use this color? 60 here. And we still have, what color did I use there? Orange. We still have 80 here. So this is still 80. And this is still 60. Okay. So if we didn't know, if I didn't tell you the wife's salary and I asked you to guess the husband's salary, you would still give 80. But suppose I tell you that the wife's salary is way down here. Here. So the wife's salary is only whatever it was last time. What was it? 20. Now, what would you guess is the husband's salary? So how about Rosim? what would you guess is the husband's salary now?
I would guess it is
Hold on, hold on, hold on, hold on,
26.7.
hold on, hold on, hold on. Let me just do one thing here. Make this a little bit more obvious. Okay, try it again.
26.7.
26.7. Why? Why?
Because because it was 60,000, then you made
That,
it
that-
20,000.
wait, let me just say it clearly. The wife's salary was 60 before, right? Now I'm saying, I'm sorry, no. The mean of the wife's salary was 60. What's that noise? The mean of the wife's salary is 60, but but I'm saying, suppose that we have a wife and her salary is 20, and I'm asking you, her husband, what would you guess her husband's salary is? And you said 27 something? And why is that?
Because between 60 and 20, it's like 3 times
Oh,
less
okay.
wife salary
Right,
became.
right. Okay. Oh, I see. Oh, right. Okay. So he said, well, this is the distance from here to here is like 2/3, right? This is from 0 to 60, and 20 to 60 is 2/3 of the way down, he said. So he said, well, I should go 2/3 of the way down here. So 2/3 of the way down here, he estimated, was about 27 or something. Okay, that's an interesting, good answer. Basically, not the right answer, but it's a good answer. So he said something like, well, I'm going to guess that it's 27. Okay, so that's good. But the thing is, he's not recognizing the important thing that I'm trying to show here. That is the difference between this picture and this picture. So what is the obvious difference between this picture and this picture? What am I trying to say with these two pictures? I drew these pictures. What do you think I'm trying to say when I drew them? Somebody different. What's the difference between these two pictures?
The second graph doesn't have strong correlation.
Yeah, the second graph, I wouldn't say that the husband and wife salaries are related. Okay, well, what do I mean by that? I mean that if I know that the wife's salary is low, that doesn't give me any information about the husband's salary. The husband's salary could be way down here, but it could be way up here. Look at the couples whose wife's salary is 20, and you have all of these possibilities. There's no reduction there's no change in what I should predict, whether it's 20, 50, 60, 70, 80, 90. There's no reason why I should predict this high or this low or anything else. So for this picture, again, the best guess would just be the middle. For this picture, the best guess would just be 80. This data doesn't say anything about how to improve my guess, but here it definitely does. Here it definitely does. If the person if the wife's salary is 20, the spread is only like from here to here. So right in the middle of that might be about 30. So I wouldn't guess 80 in this case, because I know that the wife's salary is very strongly related to the husband's salary. So that's what I mean by related. It means that if you know the x-axis that will give you a good indicator of what the y-axis should be, or I'm sorry, if you know the x-coordinate, that will give you a good indicator of what the y-coordinate should be. So if the x-coordinate is very low, I'm going to predict that the y-coordinate is also low. Now, we could also have a picture like this. We could also have a picture like this. And the dots might look like this. So how about these? Are these related? The x and y coordinate, are they related?
Yes, they are related.
Yeah. In other words, if I know that the wife is very low, I'm sorry, very high, then I would guess that the husband is very low. So this gives me a lot of information. Because if this is high, I definitely would predict low here. So there's a lot of information in these green dots. We say they're very strongly related, or they're very strongly correlated, or not the dots are correlated, the two quantities, wife's salary and husband's salary, are strongly correlated here and also here, but not here. Here, the correlation is like nothing. We actually say here the correlation how can I change the size of this thing? I just don't know how to do that. I guess I have to just make it bigger. There. The correlation is 0, or basically 0 here for this picture. The variables husband salary and wife salary are not related here. Here, we're going to say the correlation is maybe 0.88. So that's very, very strong. And here, it's even stronger, really. So here I might say the correlation is maybe, but it's negative. We say it's negative 0.93 or something like that. Just making that up. But this is more strong, actually, than this one. But it's just in the negative direction. The slope is positive here, but the slope is negative here. So we say negative 0.93. Now, if we had something like this, oops, we had something like this, I probably won't draw it that well, but let's say we had this. This data, we might say the correlation is 1, means perfect straight line relationship. So we might say the correlation is 1. Okay? So what do I mean by that? That means that if I know the wife's salary, I can predict exactly what the husband's salary is. No, there's no play. It's not like could be up here and could be down here. If this is the wife's salary here, then I'm going to predict exactly this for the husband's salary. There's not going to be any guessing. the data is completely correlated. There's no mistake if I make this guess. Whereas here, we expect there's some kind of some error here. So if this is the wife, I'll predict I'll go up to here, and then I'll go over to here, and I'll say that's what I predict the husband is. But I recognize that it's more like between here and here. It's not I don't get a perfect prediction here. Okay, so this is not perfectly correlated, but this is perfectly correlated. So if it's a perfect straight line relationship like this, the correlation will be 1. If over here, the correlation is not perfect, and I said maybe it's 0.88. And over here, the correlation is not perfect either. It's better than the other one, but it's 0.93. In this case, negative 0.93. Okay, now the question is that we were working on last time was how do we measure correlation? Where do these numbers come from? So we have, let me take, say, which picture? I'll take this picture, but I'll add a few more dots here. Okay, so suppose we have that. And so suppose we have that. Now, where does this number come from, 0.88? So what we said, we can divide this up into quadrants. So we'll call, let's say here, I'll call this quadrant 1. I'll call this quadrant 2. I'll call this quadrant 3. And I'll call this quadrant 4. Okay? So now we can make some observations about the dots in quadrant 1, the dots in quadrant 2, the dots in quadrant 3, and the dots in quadrant 4. But we have to, first of all, we need a formula. And if you recall from last time, we had this picture here. We had this picture, and we had a formula here. Where was it? Here, this formula here. So let me take a snapshot of that and put it in ours. Put it here maybe if I can. Okay, there. So we're going to think about this calculation. We can ignore this bottom part. We're not going to worry about that right now, but just the top. So if can I blow this up? Yeah. So you can see in here, I'll just write out those pieces. So you can see that we have a x I minus x bar there. And we also have a y I minus y bar there. So we want to focus on these. So remember, here's the x-axis and here's the y-axis. And here is x bar. We said that the mean for the x coordinates was here, and the mean for the y coordinates is here. So this line represents the mean for the y coordinates, and we draw a line here to represent the mean for the x coordinates. And then we're going to calculate for each dot. Remember each dot. So here's a dot. Maybe I should use this color. Well, I think I am using that color. So I could take this dot here, right here, and I could say, what's its x coordinate? Maybe this is what? Let's say 70. And I could say, what's its y coordinate for this dot here? And I would say it's, why can't I draw there? Oh, well, I don't know why that doesn't stay there, but I could say that is maybe, let's say, make it 90. So I'm talking about this dot here. Okay, so if that's true, if I take this, the x coordinate, so this is the x coordinate here, call this xi, and this is the y coordinate, yi. So if you take xi minus x bar, so xi is 70 and x bar is 60, so 70 minus 60 is 10. But I don't care that it's 10, I just want to say that it's a positive number. So 70 minus 60 is a positive number. And then I can do the same thing for the y coordinate, 90 minus 80, that's also positive. So for a dot, and that's going to be true for any dot in quadrant 1. If I take any dot here and take its x coordinate minus x bar and its y coordinate minus y bar, for every dot in here, they're both quantities. Both of these are going to end up being positive. And so when I multiply them together, it's going to be positive. So what I'm doing here is I'm doing this for every dot. So I take a dot and I find its x and y coordinates and I calculate this product here. And then I'm going to sum it up, means sum it up over all the dots. So not just this dot, but every dot. I'm going to do this. So whenever the dots are in quadrant 1, the things that I'm adding into this sum are going to be positive. Now let's talk about a dot here. Suppose we have this dot. So if we take its x coordinate and its y coordinate, so let's say this one has a x coordinate of, I'll just make it up, 50, and say this has a y coordinate of 40. So now if I want to do this calculation again for the purple dot, I'm going to take 50 minus 60. That's a negative. And I'm going to take 40 minus 80. That's also a negative. So when I multiply those two together, I'm going to get a positive. So whenever I take a dot in here and add its contribution to this sum, I'm going to get something where I have a negative times a negative. That's also going to give me a positive contribution to this sum. Now, what about quadrants 2 and 4, though? Are they going to give positive dots? Are the dots in quadrants 2 and 4 going to give positive contributions to this sum? Well, let's think about it. So let's take an orange done in quadrant 4. So let's say this one. What are its coordinates? So its coordinates might be, this might be 70 for the x. And this is going to be less than 80. So let's say it's also 70. So when I do this calculation for this dot in the quadrant 4, I'm going to get 70 minus 60, that's positive, but I'm going to get 70 minus 80, that's negative. So when I multiply these two together, that's going to give me a negative contribution to this sum. So in quadrant 4, that's true for every dot in quadrant 4. So it's going to give us negative contributions to this sum. And what about here? So let's take one more. So let's take this one, a dot here, so like this one. So if we look at its coordinates, so the coordinates of this dot, the x coordinate is going to be less than 60, so let's say it's 50. And the y coordinate is going to be more than 80, so let's say 90. It's really not 90, but let's say 90. Okay, so now when we do this calculation for a dot in this quadrant, we're going to get 50 minus 60 is going to be a negative, but 90 minus 80 is going to be a positive. So that's going to be a negative times a positive here, and that's going to give us a negative contribution. So if a dot is in this region, it's going to give a negative contribution. Okay, so with all of that, we see in here we're going to get positive, here we're going to get a negative contribution, dots in here are going to give us a positive contribution, and dots in here are going to give us a negative contribution. So what about if we had this picture like this? Well, if we drew these lines here like this, it might look like that, and it might look like this. So where are these dots? These dots are all in either quadrant 1 or quadrant 3, right? Does everyone see that? Maybe I didn't really draw it that well. This should be up higher. So excuse me for doing that. But basically you can see what I'm trying to say, which is here's quadrant 1 and quadrant 3. And what I was trying to show, although I didn't do it very well, is that all the dots are going to be either in quadrant 1 or quadrant 3. That means they're all going to make positive contributions to this sum. Does everyone see that? Now, what if the dots weren't like that, but they were like this? For the red dots, if we had data distributed like the red dots, what would the contributions be, positive or negative?
Negative.
What?
It would be
Negative.
Negative, right? Right. They would only give negatives. So when I do this sum for the green dots, I'm going to get all positive numbers in here. So this is going to be, for the green dots, this would be a large positive number. For the red dots, all the contributions are going to be negative. So this would be a large negative, sorry, this would give me a large negative number if I did it just for the red dots. Does everyone see that? Now, what happens if the dots look like this? Then what? I'm going to get a lot of positive here, a lot of negative here, a lot of positive here, and a lot of negative here. So what's the total going to be? A lot of positive, a lot of negative, a lot of positive, a lot of negative. What's the total going to be? For this kind of configuration. So all these are going to give me many positive numbers in that sum. Remember, we're talking about this sum. We have
Would
two
it
parts.
would it be 0, Professor?
Yeah, it's going to be like 0, right? Because I'm going to get a lot of positive numbers from these dots in this sum, and then a lot of negative numbers from these dots, then a lot of positive from these, and a lot of negative from these. And when I add up all those numbers, I'm going to get a lot of cancellation. So this is now, for this kind of configuration, this sum is going to be close to 0. Okay, but for the other ones, it was going to be here, it was going to be very large positive number. And here, or sorry, here, for the green dots, it's going to be a very large positive number. For the red dots, it's going to be a very large negative number. So this sum tells us a lot about the configuration of the dots. So if I get like perfect positive correlation, this sum is going to be big. If I get perfect negative correlation, this sum is going to be a large negative, big but negative. But if I get no here where this is no correlation in the data, this sum is going to be 0. So this sum is very important in terms of what kind of relationship the two variables have. Here, the two variables have no relationship, and this sum is 0. For the green dots here, they have a very strong relationship, and this sum is going to be a big number. And here, when the dots look like these red ones, which means there's a very strong correlation but negative, this sum is going to be a big negative number. So this sum is really important. It tells me whether the data is related or not, whether the variables are related, whether there's a correlation between them. Now, there's just one little problem with this summation here, and that is, maybe like in this green one, I might get, suppose for the green one here, when I do this sum, I might get 1,000. Let's just make that up. And if I did it for the red one, let's say, I might get, let's say, negative 1,000, for example. But those numbers, 1,000 and negative 1,000, those are kind of like sort of arbitrary. They kind of depend on how many dots are there. So I don't really want that. So I like the fact that this is very large and positive. I like the fact that this is very large and negative, but I'd prefer that this calculation always be between this calculation or the calculation I do, I would prefer that it's always be between -1 and +1. And these are not. This is like 1,000 and -1,000. They're not always between -1 and +1. I want to construct something like this, but that only goes as high as +1, not as high as 1,000 or 10,000 or 10 million, and only goes down to -1. So that if the relationship is perfect, like these green, it'll be 1. And if the relationship is perfect, but like these red, but negative, it'll be -1. So I'd like to have this calculation, but to kind of scaled down so that it's always between -1 and +1. And that can be done by this. Taking this and dividing it, not by this, not this, that's not what I'm going to do, but dividing it by, let's see if I can erase this. No, but I can maybe move it. No. Okay. So I'm going to divide it by, so I'm going to use this calculation, but I just want to scale it down. So the way the way that this, the good thing to divide it by is, wait, do we have that notation? No, we don't use that notation. Sorry. Let's do, I think we have this notation. What does this notation mean? I think we have this. What does this one mean? What's this mean? Don't we have that? Can anybody tell me what that means? We learned that.
Variance.
What?
Variance.
Variance? Well, not quite the variance.
Standard deviation.
It's the standard deviation. This is the standard deviation, and this is the standard deviation. So do these mean the same thing? This and this, are they the same? Does this mean the same thing as this? Does the one with the purple mean the same thing as the one with the orange? Do they mean the same thing?
Yes.
Really?
Mm,
They don't look the same.
one for
This-
X and the
This
other
says what? Sigma what?
for X,
X, and this says what?
Y.
Sigma Y. So they're not the same, right?
Yeah.
So what does sigma X mean? The standard deviation for the X data, right? Remember, we have each of these dots has an X coordinate. Or we can say each of these dots has a wife's salary. So we have all the wives' salaries, and we can calculate the standard deviation of their salaries, right? Does everyone understand? Right? We can take all the wives' salaries and calculate their standard deviation. Why not? We just collect them and then put them in Excel and calculate the standard deviation. It's easy. And then what else can we do? What does this stand for? What does this stand for?
Standard deviation for Y.
The standard deviation for Y, and in this case, Y is the husband's salary, right? So we can also take all the husbands and ask them what their salaries are, put that into Excel, and calculate that standard deviation. So what am I saying? We said that this sum here is really important for telling us what the relationship is between the two variables. Whether they're correlated or not, and how strongly correlated are they? So are they correlated like 1, or are they correlated like, what did I say this one was? Are they correlated like 0.88? Are they correlated like 0.93? This was really important for doing that, but it wasn't bounded. So this could be as high as 1,000, or as low as negative 1,000, or even larger than 1,000. Could be, it's just can get really big. We don't really want that. we want to make sure that the calculation is always between +1 and -1. This will do that. If you put these two in the bottom, divide by these two, that scales everything down. And it will scale it down to exactly between -1 and 1. So the green one, when we do this calculation, will be, if I drew it perfectly, will be 1. The correlation will be 1. And the red one, if I drew it perfectly, the correlation will be -1. So this is the correlation coefficient, it's called, or this is this number, 1.88. These are called the correlation coefficients. Correlation coefficient is -0.93. Correlation coefficient is 0.88. Correlation coefficient is 1. Correlation coefficient for the red one is -1. Correlation coefficient for this one is 0. Okay, and what's the calculation for the correlation coefficient? It's right here. Okay, so this, now maybe I shouldn't have used sigma here. I should have used S sub x and S sub y, because maybe I'm only talking about a sample of data, and I only used x bar here and y bar, so I guess I should have said S sub x and S sub y. If I had used mu x instead of x bar here and mu y instead of y bar, then I would use sigma and sigma. So maybe I shouldn't have put sigma in there. I should have used S. But anyway, the idea is here. Okay, so here is the correlation coefficient, and it's usually called R. So we would say that R here this is R, 0.88. Or we would say here that R for the green one is 1. And we would say that R for the negative dots is -1. And we would say here R for these dots might be -0.93. And maybe R for here might be 0. Okay, so that's what but R, this is R. This is the formula for R right here. R equals this orange formula here. This is the definition for R. And we can see where it comes from, because we did all these things where we looked at the first quadrant, the second quadrant, third quadrant. We saw that if all the dots are all in here and here, it's going to be a large number, and so on. Okay, so that is called the correlation coefficient, and you can easily calculate it in Excel. Let's just do an example of that. Let's just do Excel. And let's say, let's suppose we have some data like this. Let's suppose we have fertilizer, and we have crop output. So let's suppose, we have like a field or many fields. Let's suppose we do an experiment where we have many fields. We have a big plot of land and we divide it up into fields. We got a bunch of fields. They don't all have to be the same size, but we have a bunch of fields. Like that, and another like here, and another one like here. Well, no, sorry, let's say they're all the same size. Sorry about that. Let's say all the fields are the same size. And then we're going to put some different amounts of fertilizer in the fields. So here we're going to put 100 pounds of fertilizer. And here we're going to put 200 pounds of fertilizer. And here we're going to put 800 pounds of fertilizer. And here we're going to put 300 pounds of fertilizer. And here we're going to put 200 pounds of fertilizer. And here we're going to put 500 pounds of fertilizer. So we're going to put on all kinds of different amounts of fertilizer in the field. And let's say all these fields are the same size. And then we're also going to, so we're going to do that at the beginning of the summer or in the spring. And then at the end of the summer, we're going to figure out how much rice we got from each field. So let's say, you know, in this field, we got, you know, 1,000 bushels or whatever of rice. And here we got 2,000. And here we got 3,000. And here we got 2,000, whatever, right? We have a bunch of results. How much rice we got? Here we got 8,000, whatever. Okay, so we have this scenario. So let's make up some data. So we're going to put in fertilizer. Let's say we put in 100 in one field and 200 in another field and 200 in another field, 300 in another field, 500 in another field, 800 in another field, 500 in another field, 400 in another field, 900 in another field, 500 in another field, 2,000 in this field, whatever. Okay, and then we do the crop output. So here there was 50, whatever it is, 50 bushels of rice, and here there was 80 bushels of rice, and here there was 90 bushels of rice, and here there was 150 bushels of rice, and here there were 300 bushels of rice, and here there were 400 bushels of rice, and here there were 200 bushels of rice, and here there were 500 bushels of rice, and here there were 1,000 bushels of rice, and here there were 800 bushels of rice, and here there were, let's say, 1,200 bushels of rice. Okay, so we have two variables, X and Y. X and Y. So we might ask, are these related? Is there any correlation between them? If we know how much fertilizer is put into the field, does that help us to predict what the crop output is going to do? Or is there no relationship? Okay, does everyone understand? We want to figure out whether there's a correlation here or whether there's no relationship. So we can figure out the correlation coefficient. Let's see what it is. Let's say, how do we do it? We look up here. We look under statistics. We look for correlation. And I think I saw it here, correlation. And we click OK. And I think we just put, whoops, sorry. I don't want a value. I want no space between these two. Okay, so let's try that again, correlation. So we're wondering, are they related or not? And what, if they are related, or what's the correlation coefficient? So let's see what it is. So let's click that. And I think this works. Let's see. You're going to, maybe we have to do it differently. Let's do that again. Try that again. Maybe it has to be here. I'm not sure. Like that. And here. Okay. Ah, there it is. So there it is. So it's a pretty strong correlation between the fertilizer and the crops. So if you want to see a picture of this to sort of verify that, you can do a graph. So insert it's going to be like this kind of graph, like this. Whoops. Have to select the data first. And then try that again. So that's the data. So there's a kind of strong relationship between the X value, the fertilizer, and the crop output. Okay? And the measure of it is 0.84. Does everyone see that? And we see where this comes from. We see the definition, or yeah, the definition of this. We see where this formula comes from because of this analysis of the quadrants. Okay, does everyone get that? Now suppose the data look different. Suppose that it looked like this. Let me just change this. Let me just make some new data. Let's say, I'll still say it's X and Y, but suppose it looked like this. Let's say 100, 200, 300. Let me just do this like this. Okay, like that. And suppose that the data looked like let me see. Okay. Suppose the data looked like this. Oh, wait, no, I don't want that. No, I didn't do that right. Right, yeah, I'll leave it like that. So suppose the data looked like this. Okay, so I have some fertilizer and some crop output. Okay, and this is my data. Okay, now let's draw a graph of this data. So let's draw a graph of it. Like that. Okay, that's sort of what I want, but not quite. I want a little bit different than that. Let me try one more. Let me try it once more. Okay, let me try again. To make this graph with this data. Try with this graph. Not quite what I wanted either. I'm going to try one more try here. Once more. We just do this one more time. Okay, so this should be good enough for what I want to show. Okay, let me try it again. And the graph here. Okay, there. Okay, so does everyone see the graph? So would you say that fertilizer is useful in predicting crop output from
Yes,
that
yes,
picture?
sir.
From that picture?
Yes, yes.
Would you say that it's useful in predicting crop fertilizer is useful in predicting crop output? So remember, we said that in this picture, why is this not moving? Remember that we said in this picture, knowing the wife's salary was not useful in predicting the husband's salary. If I know the wife's salary is down here, I still have a huge range for what the husband's salary could be. So going back to this data, if I know that the fertilizer is here, is it useful in predicting the crop output or not?
Not quite, because they're nearly the same value.
Well, they're not nearly the same value actually, but it doesn't matter if they're the same value. It's just, is there a lot of play in this data or not? No, there's like no play. So if I know that the fertilizer is 1500, I can be very clear, very sure that the output is going to be this height. There's not a lot of, this data is very clear. Does everyone see that? This pattern is very, very, very clear. Does everyone see that? So there's no play here. I don't have dots up here and dots down here and dots here and dots here. I don't have a lot of spread around this curve. I have just a very clear curve. Does everyone see that? Whereas if I had done this, if I had changed the data to look like this, how about now? Watch this. Now watch what happens. Now there's more play, right? You see that? And let me do it even more. Let's try this. Okay, now there's even more play. So now I'm not so sure if the fertilizer is here. Should I predict way down here or should I predict way up here? So now I don't have anywhere near the clarity I had before when it looked like this. Now I have no play. If it's 1500, it's not like it's going to be up here or down here. It's going to be exactly here. Does everyone see the difference? Again, if it's like that, I have a lot of play. I can even make it worse, I guess. See here. So anyway, it's supposed to mean that there's a lot of play and I'm not sure about the predictions. Does everyone get this? So this correlation, let's see what it is. Maybe I'll go back to the other one for some reason to look better. This correlation, let's check to see what the correlation is in here. No, sorry, that's not what I want to do. Sorry. let's go back to my original picture, which is this picture. Okay, that's the picture I had, and I said that the two variables are very strongly related. Very strong relation here. So you might think that means R should be very close to 1. For example, it should be like 0.99. I'm sorry, 0.99. You might think that, but it's not going to be that way. Let's see. Let's check it. Check the correlation here. Correlation here. Let's see what it says. Whoops. Sorry. Try that again. Check the correlation here and here. And let's see. Well, it's still pretty strong actually, but I thought it was going to be 0.99, and it's still very high, but it's not 0.99. Okay? So the thing you have to understand about correlation coefficient, this R calculation that we're talking about, the thing you have to understand about this is it doesn't measure non-linear relationships. So this is a strong relationship, but it's not a linear relationship. It's not a straight line. Correlation coefficient only measures, so if I was just measuring the relationship here, it would be about 0.99, but it's not. That's not what the correlation coefficient measures. It measures the linear, measures how close to a straight line is it. And this data is not close to a straight line. It's a curve. So correlation coefficient for this is not going to work, or it's not going to work very well. So you have to remember that the correlation coefficient only measures the linear relationship between the data. So going back to here, it's only measuring the linear relationship. Here, this is a perfect linear relationship, so it will be 1. This is a perfect linear relationship, so it will be -1. But it only measures linear relationship. Even if the data was like perfectly related, but if it looked like this, so it's very clearly related, but the linear relationship is not good. This does not fit a straight line at all, or there's no straight line that I can draw that's going to fit this data very well. So this does not, so the correlation coefficient for this would probably be like, 0.2 or something like that, even though there's a very strong relationship, but it's not a linear relationship. So you need to remember that this R measures linear relationships. Okay, so we've finished with that now. Are there any questions about correlation coefficient? So if we go to our book, we can see that there is some discussion of correlation.
Professor, sorry to interrupt.
Yes.
Everyone, please do respond for today.
Okay, great. Thank you. So what happened? Let's see, it's here. And we go down to section 3.5, and here it is, the correlation coefficient. And it's given here, and this really is exactly what we just wrote. So this symbol at the top is just that summation that we've been working with. It's right here, this part here on the top. So this, they use this, the notation for that. This is called, in this book, the top here is called S, X, Y. And this, they don't use sigma, they use S. So this is here, and this is here. So what we have, what we expressed here, they're expressing as S, X, Y over S, X, S, Y. Okay, so that's exactly what we have here. Okay, they're just using this notation, SXY, for this top piece. Okay, so that's what we have, that's what we did. So you should be able to read through this now and understand it. Now, I said I used R here. I said use R, but R is if everything is sample, just like when we use S versus sigma, S for sample, sigma for population, and we use X bar or mu. So for this correlation coefficient, we use R, but we also use the Greek letter is rho. That's a Greek rho. So we use either this one or this one. This is a Greek rho, and this is R. So if you're using population, you use rho. If you're using sample, you use R. So they have that here, rho, and so on. Okay, and here's R. Okay, and so this one is going to be a perfect positive linear relationship. So this will have an R of 1, or I don't know, they're using rho. Well, here, R is 1. Okay, and then this one now, what's the R going to be here? Anybody want to make a guess? Any guesses here for the R? Is this linear? Is this picture linear?
No.
No. It's like a parabola, right? Looks kind of like a parabola. So that's not linear. Okay, so R is not going to be good here. R might be even 0. I don't know if it's really 0, but it's not going to be very high. Okay, so it's almost 0 here, 0.007. So that can be really misleading. Some people will just jump to the conclusion, oh, R is almost 0 here. That means there's no relationship between the temperature and the amount of money that people spend to stay comfortable. So what's going on in this picture? Why does it go high, low, high? Why does that happen? Well, think about your cost, how much money you spend to keep your room comfortable. What happens? What about the cost? If it's really cold out, you have to spend a lot. So this is very cold down here. This is Fahrenheit. So this is very cold down here, so you have to spend a lot. But when it's like around temperature like this, you spend nothing or not much. But when it gets to be this temperature, which is like 35 degrees Celsius, you have to spend a lot again if you're going to use an air conditioner or cooler. Okay, so there's definitely a relationship between the temperature outside and the money that you spend on, air conditioning and heating. There's definitely a relationship, but it's not a linear relationship. But if you just looked at this R, you'd say, oh, there's no relationship. But you can't misinterpret this R. You have to recognize this is only checking the linear relationship. It's only checking the linear relationship. So that's why it might be 0 here, or close to 0. Okay, we did that. Okay, that's it. Okay, so we finished chapter 3. So now we have to go to probability. So we have to study a new subject. So sometimes we say the course is called Statistics and Probability. So there's one study which is statistics, and then a separate field called probability. But here we're just calling it all statistics, but it's really, we're doing two kind of separate fields here. One is statistics and the other is probability. Of course, they're related though. So we're going next to chapter 4. So let's see if we have any video and any questions relating to this. Okay, let's go to here. Our study. Okay, so we want to start our study of probability. So let's think about when probability might arise in the real world. So let's think about managers and how they might base their decisions on the analysis of what we would call uncertainties. So often managers face uncertainties, such as this one, the first one. What are the chances that the sales will decrease if we increase the prices? So the chances, that's going to mean probability. What is the likelihood that so the first one is, if you're the manager of a company, you might want to increase your prices, but you also might want to guess beforehand whether or not the sales will decrease. And you might try to calculate the probability that sales will decrease. So that's one example where the word probability comes up in business. So the chances, that's going to mean probability. What is the likelihood that a new assembly method will increase productivity? So here again, likelihood, basically probability. And this is a little bit different than probability, but basically the same thing. What are the odds that a new investment will be profitable? So these situations certainly occur everywhere and all the time. We're always faced with uncertainty. And probability sort of enables us to deal with uncertainty sometimes by treating it mathematically. So we might talk about what's the probability that it's going to rain tomorrow, Or what's the probability that I roll a 6, that I get a 6 when I roll a die? Or what's the probability that the stock price will move up? Or what's the probability that sales will increase if we take some kind of measures in our company? So what do we mean? What do we mean by probability? So in mathematics, we're going to say probability is a number. It's going to result in a number. For example, when we say what's the probability that it's going to rain tomorrow, we might say 50%, or we might say 20%, or something. So it's some kind of number. So the number should always be between 0 and 1. We never say the probability that something will happen is 150%, right? So it's always between 0 and 1. So probability is a numerical measure. So it's kind of, when we say the probability that it will rain, we're kind of measuring the probability of that event. In that case, the event that it will rain, or the event that sales will increase. What's the probability that sales will increase? So we're trying to talk about the event that sales will increase and assign a number to it, like the probability that sales will increase. We might say the probability that sales will increase is 80%. Or we might say the probability that it will rain. So the event that it will rain, we want to assign a number to that event. We might say 20%. So they say probability is a numerical measure. It's a number assigned to an event. And probabilities are always assigned on a scale from 0 to 1. So they are a numerical measure assigned to some event, like the event we said can be that it will rain, or the event could be that sales will increase, or the event might be that we get an even number when we roll a die. So you know what we mean by a die. Right? We have a die, and we might get an even number when we roll it. So that's an event, right? Whatever. Okay, so that's another event that we would get an even number. Or, like we said, the event that sales will increase, or the event that it will rain. So those are we talk about events, and we just mentioned 3 of them, and then we assign a number to the event. That number is the probability. So the probability that it will rain is a number, 20%. So we'll write that as 0.2. The probability that we get an even number, maybe we'll say it's whatever, it doesn't matter what, I mean, maybe we don't know what it is, but let's pretend that it was 0.5. So that's a number that we assign to that event, and that we call that the probability, or the probability that sales will increase. Let's say we give that a number, let's say 80%. Okay, so we have events, and then we assign probabilities to them. And the scale is always between 0 and 1. And a probability near 0 indicates that the event is unlikely to occur, and a probability near 1 means that it's almost certain to occur. So it can be between 0 and 1, and of course if it's close to 1 we think of it as almost certain, and if it's near 0 we think it's very unlikely to occur. Okay, now we want to talk about a word, and we're going to use this word experiment, and we're not actually going to, it's going to be used in a slightly different way than we would normally use it in physical sciences, like in chemistry we do an experiment, or in biology maybe, or in physics we do an experiment, but when we talk about statistics experiment, we're slightly different meaning. In statistics, the notion of an experiment differs somewhat from that of an experiment in the physical sciences. In statistical experiments, probability determines outcomes. Even though the experiment is repeated exactly in the same way, an entirely different outcome may occur. So we just talked about 3 events. We just talked about the fact that it might rain, the fact that we might get an even number when we roll a die, and the fact that sales might go up. So whenever we talk about probability and events, and these are all called events, there must be some so-called underlying experiment. So you may not think of that there's an experiment, but we want to say that there's an experiment. So in this case, this is the easiest example to say there's an experiment. The experiment is to roll a die, to take one of these dice and roll it on the floor, and then see what will happen. So we call that the experiment. So in this case, it's easy to understand that could be called an experiment. You just throw the dice on the floor and then see what face occurs. So we talk about an experiment, and then we talk about the set of outcomes that are possible for that experiment. So if we roll a die and we call that an experiment, and then if we want to think about the set of possible outcomes when we roll the die, so what are the possible things that could happen when you roll a die? What are the things that could happen when you roll a die? Everybody knows what I mean by a die, I think. Right? Something like this. So when you roll a die, what can happen?
Like a 1 out of 6 chance of getting a number.
Right, but I want to know, what I want to do is list all the different possible outcomes. So what I mean by that is the different possible outcomes. What I mean is you could get a 1 when you roll the die. You could get a 2. You could get a 3. You could get a 4. You could get a 5. You could get a 6. Okay, does everyone get it? So that's called the set of possible outcomes when you roll a die. Now, if you toss a coin, then we could ask, what are the possible outcomes? Whoops. If you toss a coin, well, okay, if you toss a coin, so you know what I mean by tossing a coin. I mean like this. And when you do that, what are the outcomes?
Heads and tails.
Right. We have heads and tails. Okay, so we're going to talk about the experiment of rolling a die, the experiment of tossing a coin. And then the experiment has 6 different outcomes here. And the experiment here has two different outcomes. Okay, now I think we've run out of time for today. So I will assign some more homework over the break, and I'll see you next year. Okay,
Happy New Year, Professor.
Happy New Year to everybody.
Thank you,
And
Professor.
we're going to continue to study probability. And hopefully it should be. So in probability, we can do the calculation. I think we did it in class where we said, what's the chances that if we have 25 people in the room, what's the chances that 2 people have the same birthday? I think we tried that in our class, didn't we? I think we did. And so we can do calculations like that with what we learn in probability. Okay, see you next year.
Thank you, Professor. Happy New Year.
Professor.
See you.
Thank you, Professor. Happy New Year.
Thank
Happy
you.
New Year to everybody.